Our lesson goal for today will be dealing with groups of numbers. People group everything such as animals, cars, sneakers, and food. Today we'll understand and be able to recognize several groups of numbers. Are there any groups of numbers you already know? You may have guessed even numbers. Even numbers are numbers in which are divisible by 2 and generate a remainder of 0. Examples are 0, 2, 4, and 6. Odd numbers are numbers that are not divisible by 2 and generate a remainder of 1. Examples are 1, 3, 5, and 7. Another group that you may know are prime numbers, are numbers greater than 1 that have exactly 2 factors, 1 and the number itself. Examples are 2, 3, 5, 7, 11. A fun fact, 2 is the only even prime number. Composite numbers are numbers greater than 1 that have more than 2 factors. Example, 4, which has factors of 1, 2, and 4, 6, which has factors of 1, 2, 3, and 6, 8, which has factors of 1, 2, 4, and 8, 9, which has factors of 1, 3, and 9, and 10, which has factors of 1, 2, 5, and 10. A fun fact, 1 is neither prime nor composite. Our lesson today will be dealing with the real number system. By the end of this lesson, I will be able to. So when you see this, this means by the end of this lesson, I will be able to. By the end of this lesson, I will be able to classify, graph, and compare real numbers, find and estimate square roots. How are real numbers different from irrational numbers? That is our essential question. So let's take a look at the real number system. The first group in the real number system is called our natural numbers. Those are our counting numbers. If you were to start to count, you would start with 1, followed by 2, 3, 4, and 5, and so on. These are our counting numbers, our natural numbers, our very first group. Our second group has the addition of 0. That one extra number makes it a whole new group, no pun intended. Our next group of numbers is called integers. Integers are all the whole numbers, and if we negated them as well, made them into negative numbers. But remember, 0 is the same as negative 0. Negative 0 is 0. And our next group are called rational numbers, aka also known as fractions. Any number that can be written in the form of a over b, where a and b are integers and b does not equal 0. This also includes repeating decimals and terminating decimals. Under the real number system, you can either be rational or irrational. Natural numbers, whole numbers, and integers are all rational numbers. The other side would be called irrational numbers. Irrational numbers are any number that cannot be written in the form of a over b, where a and b are integers and b does not equal 0. Also includes non-repeating, non-terminating decimals, square roots of non-perfect squares, and the number pi.
Eureka! 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 Eureka!
Here are some examples of real numbers. The two classifications for real numbers are rational or irrational. Real numbers are either rational or irrational and cannot be both rational and irrational. You can only be one or the other. The reason why we call rational numbers rational because a ratio is a comparison of two numbers by division. 12 over 4, since we see it as a ratio or a fraction, this actually means 12 divided by 4. 12 divided by 4 is 3, since 3 times 4 is 12, and we have a remainder of 0. Terminating decimals such as 0.45 and repeating decimals such as 0.77777, ... and so on, are also rational numbers since we can write them as ratios. Let's write terminating decimals as ratios. To do so, we must remember our decimal place value chart. When we look at this number 0.45, this is actually read as 45 hundredths, since the furthest most number to the right of the decimal is in the hundredths place. So we read it as 45 hundredths. One way of writing 45 hundredths is to write it as a ratio, 45 over 100. Since the numerator and denominator are both divisible by 5, the result is 9 over 20. Let's take a look at this one. Since the furthest most number to the right of the decimal is in the tens place, we read this as 7/10. Therefore, we could write this as 7 over 10, a ratio. Since 7 and 10 are relatively prime, they do not have any common factors, we are finished. When we multiply decimals by powers of 10, all we need to do is move our decimal point to the right, depending on how many zeros we have after the 1. So in this case, we have 1 0 after 1. We move our decimal point to the right one time, which gives us 4.5. Let's look at another example. 0.7 or 7/10 times 100. Since there's 2 zeros behind the 1, we move our decimal place 2 places to the right. In this case, we need to use a placeholder after the 7 since we do not have a number there. 7/10 times 100 is 70. How many times would we have to move the decimal if we're multiplying the approximation of pi times 1,000? If you said 3 times, you are correct. 1, 2, 3. The result is 3,141 and 59 hundredths. Let's write repeating decimals as a ratio. When we take a look at this repeating decimal, we have to use the 3 little dots to form an ellipsis. This means and so on. An easier way of writing this, 0.7 bar, which means the 7 continues forever, 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 forever. It never stops. So since the 7 to the right of the decimal goes on forever, if I multiply it by 10, will the 7 go on forever? Yes. If I multiply by 1,000, will the 7 after the decimal point go on forever? It will. And if I multiply it by 1,000, it will. It doesn't matter how many zeros I have, it will continue forever. This concept will help me when I'm trying to write a repeating decimal as a ratio. Always start by letting x equal the repeating decimal you are trying to write as a ratio. Since this repeating decimal repeats after the tens place, we'll multiply both sides by 10. 10 times x is 10x, and 10 to 7 continues forever. It never ends. So even though you moved it over to the right one place, you still have an infinite number of 7s after the decimal point. Well, now let's subtract this repeating decimal, which was 0.7 bar, from both sides. But instead of subtracting it from the left side, let's subtract something that it's equivalent to, which is x. It's like if Tarsus had 2 $1 bills and Ayana had 8 quarters. If I took away $1 bill from Tarsus and 4 quarters from Ayana, they still have equivalent amounts. When we do not have a coefficient, a number in front of a variable, it's understood to be 1. We can subtract. 10 minus 1 is 9. 7.7 bar minus 0.7 bar is 7. We'll divide both sides by 9. The 9s will cancel on the left-hand side, leaving us x is equal to 7 over 9. 7 over 9, if you use the calculator, you would see that you get 0.777777 forever. But your calculator approximates, it will round at the end. And remember, when rounding, 5 or more, raise the score, 4 or less, let it rest. This means if I'm trying to round to this number, I'm going to the number to the right. If it's 5 or more, I'll raise the 7 to an 8. If it's 4 or less, I'll let it rest. In this case, it was 5 or more. It raised the score. Let's take a look at another example. We always begin by letting x equal the repeating decimal. Since it's repeating after the hundredths place, we'll multiply both sides by 100. This will leave us with 100x is equal to 81.81 bar. We're moving the decimal place just over 2 places. But remember, 81 repeats infinitely after the decimal. So now we can subtract 0.81 bar from the right side and from the left. But instead of subtracting 0.81 bar from the left, we're going to subtract what's equivalent to it, which is x. We have an understood 1 coefficient. 100 minus 1 is 99x, which is equal to 81. The 0.81 bar minus the 0.81 bar will leave you with 0, so then 81 minus 0 is just 81. Let's divide by the coefficient of x, which is 99. The 99s will cancel, leaving us with x is equal to 81 over 99. Now we need to reduce. Since 81 and 99 are both divisible by 9, our result is 9 over 11. Irrational numbers, remember, are square roots of non-perfect squares, such as the square root of 10, the square root of 15, or just the number pi. Be careful, because when we take the square root of a perfect square, the square root of 64 is 8. Therefore, the square root of 64 is not irrational, it's rational, because 8 is a rational number, since 8 times 8 is 64. Let's take a look at the number 25. If we took the square root of 25, this would not be irrational, since the square root of 25 is 5, since 5 times 5 is 25. Therefore, the square root of 25 is a rational number. A special type of rational number is called an integer. Integers are all the positive numbers, negative numbers, and 0, but does not include any fractions or decimals. A special type of integer is a whole number. Whole numbers are all the positive numbers and 0, but does not include negative numbers or any fractions or decimals. A special type of whole number are our natural numbers. Natural numbers, also known as our counting numbers, are only the positive numbers, and they do not include negative numbers, 0, or any fractions or decimals. And irrationals, remember, are numbers that we can't write as ratios, and these also include our non-repeating, non-terminating decimals, square roots of non-perfect squares, and pi. A shortcut for writing real numbers is a capital R, since real numbers start with an R. Since R is already taken, we use Q for rational, since the result when we divide is called a quotient. We use Z to represent integers because it's the German way of saying number.
Zahl.
Whole numbers we use W, natural numbers we use N. Irrational numbers, well, that's another story. We don't have a letter to represent irrational numbers, and we'll address that at a later date. Let's classify. The square root of 49. The square root of 49 is 7. Since 7 times 7 is 49, 49 is a perfect square. Therefore, 49 is a natural number, and if you are natural, you have to be whole. If you're whole, you have to be an integer. If you're an integer, you have to be a rational number, and if you're a rational number, you have to be a real number. Let's take a look at pi. Pi. It just keeps going and going and going and never ending, never terminating, and never repeating. That's why we use the 3 dots, the ellipsis, in order to say pi is a non-repeating, non-terminating decimal. So therefore, it must be irrational. If you're irrational, you have to be real. Let's take a look at the ratio 7 over 2, which means 7 divided by 2. 2 goes into 7 3 times. 3 times 2 is 6. 7 minus 6 is 1. We take our remainder and put it over our divisor, which is 2. Since 2 cannot divide 7 evenly, we know we have a rational number. And if you're rational, you must be real. Let's take a look at the square root of 20. The square root of 20, wait a second, I don't know what that is. If we try 4 times 4, we get 16, that's too low. If we try 5 times 5, that's 25, that's too high. That means 20 is not a perfect square. since we cannot write it as the product of equal integers. Since it's irrational, we know it's also real. Integers. Integers are all positive numbers, negative numbers, and zero, but does not include any fractions or decimals. So therefore, negative 19 is an integer. If you're an integer, you must be rational, and if you're rational, you must be real. We have a repeating decimal. A ratio is a comparison of two numbers by division. Terminating decimals and repeating decimals are rational numbers, since we can write them as ratios. Therefore, 5.12 bar is a rational number, and it's also a real number. 0. 0 is a whole number. Whole numbers are all the positive numbers in 0, but does not include any fractions or decimals. So since 0 is a whole number, we also know it must be an integer, a rational number, and a real number. And the last one, 11. That's a natural number. Natural numbers, also known as our counting numbers, are only the positive numbers, and they do not include negative numbers, 0, or any fractions or decimals. Since 11 is a natural number, it's also a whole number, it's also an integer, it's also a rational number, it's also a real number. This concludes the lesson for today.